Now we're going to turn our attention to pollution, sewage treatment, and a little bit of instrumental analysis just to finish out this water chapter. Right, so far when we've been talking about pollution, we've talked about pollution by organic matter. If you remember, organic matter gets into the water. That organic matter is lovely food for bacteria. The bacteria then multiply because they've got a great food source. The bacteria use up all the oxygen then when they're respiring. And if they use up all the oxygen, then the fish die. Okay. We also looked at pollution by eutrophication, a similar process but not exactly the same. So say if fertilizers happen to get into the water and they have mineral nutrients in them, those mineral nutrients like your nitrogen are food for plants and also for algae, and so the plants and algae numbers increase. If you get an algal bloom, it will be short-lived, and when the algae die, bacteria break it down. And when the bacteria break down the algae, they use up oxygen again in respiration, and if they're using up oxygen, the fish will die. The next one we want to look at under the heading of pollution is pollution by heavy metals. And when we talk about heavy metals, we're referring to them having a high relative molecular mass, and examples would be lead, mercury, and cadmium. Now let's look at lead and mercury in water. So these two heavy metals are referred to as cumulative poisons, which means they can build up in your body over time and cause a level of poisoning as they build up. So how do they get into the water? Well, the main sources would be industrial effluent being discharged into the water, or if people don't recycle and they dump batteries instead, or going back a bit, or in an old house, you might have lead pipes in the house, which would leak lead into the water. Now, what are the effects of these two heavy metals? So the lead is poisonous and it can cause brain damage, and then the mercury is also poisonous. It can cause birth defects and even death. The birth defects one is interesting in that pregnant women are now advised not to eat some tinned fish in order to avoid the possibility of a buildup of mercury, because sometimes you'll have a buildup of mercury in tinned fish. And an interesting example of that would have been Minamata disease, where they had a problem in Minamata with mercury being discharged into their bay, and it was being accumulated by the fish, and then people living on the fish had serious health effects, and children born to pregnant women who were eating the fish had birth defects, and people showed symptoms of poisoning and even death. So how do you remove these heavy metals from water? Well, the method of removal is by precipitation, and here we have a few examples of that. So if you add hydrochloric acid in, it will precipitate your lead as lead chloride precipitate, which is insoluble in water. Or if you add calcium hydroxide, the lead will replace the calcium and you'll get a lead hydroxide, which is also insoluble. Or if you want to get rid of the mercury, then you need to add some sulfide ions, and those sulfide ions will again form a precipitate of mercury sulfide with your mercury. Just one other point on those: how do we even know that we have heavy metals in the water? They are mainly detected by atomic absorption spectrometry, which will be coming up at the end of these slides. Right, now to move on to our sewage treatment. So before we can think of discharging our sewage from our houses and from our industrial units, we have to treat it before it is suitable for being discharged into our waterways. The main goal of this treatment would be to reduce the BOD, the biological oxygen demand, which we've already spoken about in an earlier presentation. And the sewage goes through 3 treatments. primary treatment, which is mainly mechanical and consists of screening and settlement. Then a secondary treatment, which is a biological process, and that's carried out by bacteria in an activated sludge in a big tank. And then finally a tertiary treatment, which may or may not be done, it depends on the treatment plant. And that tertiary treatment is to remove inorganic compounds like your phosphates and your nitrates from the water. And all of that is done before you can say that the water is clean enough to be discharged into a river or waterway. Right, so looking at our sewage treatment in slightly more detail then, the primary treatment, first of all, we mentioned was a mechanical treatment. The definition of the primary treatment is a mechanical process in which large particles are removed by screening and some suspended solids are removed by settling. So screening, we've already come across way back at the start of this chapter when we were looking at water treatment. Screening involves passing the sewage through steel bars and they remove all the large solids out of it. Then the sewage is passed through some grit channels and that gets rid of smaller particles that were suspended in the water. And then finally, settling happens. And in settling, the water is allowed just to stay still because some fine particles that would have been suspended in the water will be carried on by the energy of the water when it's flowing, but once the water is left to stay still, they will settle out at the bottom of the water. And that little sludge that's left at the bottom of the settlement tank, or sedimentation tank as it's sometimes called, can be removed and spread on land because it tends to be quite high in nitrates. It's a good fertilizer. Now, by the time we are finished with all of this process, the screening and the settling, so we're finished our primary treatment, half of the suspended solids have been removed from your water. And with that, of course, you have removed a lot of the material that would create an oxygen demand. So you're roughly at 1/3 of the biological oxygen demand removed. Next, we're going on to the secondary treatment. Secondary treatment, as I mentioned, is a biological process. The definition is biological oxidation process in which the levels of suspended and dissolved organic material are reduced by aerobic bacteria. Okay, and this is also known as an activated sludge process. And you'll see the diagram here has a big tank, and in that tank you have a large population of bacteria. The tank is kept aerated by having a rotor in there which maintains the oxygen levels for the bacteria, and those bacteria and some other microorganisms break down any organic matter that is still left in the water. Now this liquid then flows back into settlement tanks after that and is stored there for a little bit, and by the time we get through the secondary treatment, the biological treatment, we have up to 95% of the biological oxygen demand removed. So we're getting pretty clean at that stage. Now, some treatment plants have a tertiary treatment, which is a chemical treatment, and it centres around the removal of nitrates and phosphates. So the phosphates are removed by precipitation, and that is brought about by adding aluminium sulfate, and then the aluminium sulfate actually forms phosphate of aluminium, and that aluminium phosphate is a precipitate. It's not soluble in water, so it precipitates out. You can also bring about a similar process by adding either iron 3 chloride or adding lime. And then finally the nitrates. And just again to mention, this is not carried out in every treatment plant, but the nitrates that are in there as ammonia or nitrate compounds are broken down by denitrifying bacteria, and they convert them into nitrogen gas. Now again, that's not carried out in all plants as it's an expensive process. So that's your tertiary treatment. At the end of all that, your water can be discharged into a waterway. Now this brings us to the last part of our chapter, which is water analysis. Now, We've already done a certain amount of water analysis. We looked at hardness in water and we looked at dissolved oxygen and biological oxygen demand. In addition to those two, you will have to know about three instrumental methods of water analysis, and they're fairly straightforward. The first one is pH, and the instrument that's concerned here is a pH sensor, and we've seen these before hooked up to a data logger usually. And the principle on which they work is that the voltage generated in that sensor is determined by the hydrogen ion concentration in the solution. That reading then is converted to pH. If you remember from our pH chapter, pH is the negative log to the base 10 of the hydrogen ion concentration. So once you've detected the hydrogen ion concentration, you can give a readout on your data logger of the pH. Normal water would be around 7.2. That's the proper pH for normal water. If you happened to be in a limestone region, it could be a bit higher, it might be up maybe 7.8 or that. And if you're in a clay region or in a boggy region, it could be considerably lower than the 7.2. Then our second instrumental method is our atomic absorption spectrometry. And your instrument here, which we also in DCU, was the spectrometer. Now, the principle on which this one works is that atoms from different elements absorb light at different wavelengths, and how much light they absorb is dependent on their concentration. So the higher the concentration of a particular element, the more light will be absorbed at that particular wavelength. And we mentioned earlier in this presentation that these are used to detect your heavy metals, such as your cadmium, your lead, or your mercury that we had looked at earlier. Okay, and then finally colorimetry. And there's an experiment on this one in your book. So colorimetry uses one of two different pieces of apparatus, a comparator or a colorimeter. Now, there's a vast price difference between the comparator and the colorimeter. The principle then is that the amount of light absorbed by a coloured solution is proportional to the concentration of the solution, and it's used to estimate in particular the amount of free chlorine in water. Now, there is an experiment that I'll put up a link for in your class notebook, and it's to estimate the concentration of free chlorine in water. Just to give you a quick overview of it, so chlorine is added to your pool water because it's an excellent disinfectant. It's not added as chlorine though, it is added as compounds that will form hypochlorous acid, and then the pool water should have enough chlorine in it to disinfect it, but not too much chlorine, because if you've too much chlorine you will have sore eyes. If you've too little chlorine, obviously the bacteria will flourish in your pool, and that's not a good thing either. Now, to detect then the level of free chlorine in the water, you could use this hack test, and that hack test kit is based on a comparator, and I'll just go through how a comparator works here. So you have a reference tube and you fill that with deionized water, and that's for comparison. You put that into your comparator, then you fill the other tube with the swimming pool water that you want to analyse, and you add some DPD from a little sachet that comes with it, and the DPD will react with the chlorine to form a coloured compound. You make it uniform by stoppering the tube and swirling it, and that will cause the DPD to mix with the water properly, and you'll get a pink compound. Just how pink it is depends on how much chlorine is there. So then you place this tube into the comparator with your reference tube that you've already put in, and you put in the comparator disc. Just have a quick flick back to show you the disc there. There's your comparator disc. Then you hold it up to the light and you turn that pink disc until the colour pink on it matches the colour of the solution. and then you can read off the corresponding chlorine concentration, which is given in parts per million. So that's how your comparator works. Now, that is it for the water chapter, and I'll leave it there, except that I'll add on a link to that experiment. I'll put that into your class notebook.